The first topic that we are going to discuss today is first shifting theorem. First shifting theorem. First shifting theorem. Also called S shifting. First shifting theorem. Okay. And what does the theorem say? The theorem says that if capital F of t has the transform small f of s, where s is greater than k for some value k, then e to the power at f of t has the transform f of s minus a, where a is a constant, and within bracket where s minus a is greater than some k. In formulas, this can be written as Laplace transform of ft is f of s, then Laplace transform of e to the power at f of t. This is equal to f of s minus a. This is the theorem. This is called the S shifting theorem. Okay. So if Laplace transform of capital F is small f of s, then the Laplace transform of e of t capital F is f of s minus a. Okay. If we take the inverse on both sides, we have e to the power at ft. This is equal to the Laplace inverse of f of s minus a. Okay. So we can prove this theorem. Proof. We have f of s minus a is equal to, by definition, it is 0 to infinity e to the power minus s minus a t f of t dt. This can be written as integration from 0 to infinity e to the power minus st e to the power at f of t dt. And from the definition of Laplace transform, this is nothing but the Laplace transform of e to the power at ft. So this is Laplace transform of e to the power at ft. So this is the proof. Example. Laplace transform of e to the power at cos omega t. What will be the answer? What is the Laplace transform of cos omega t? The Laplace transform of cos omega t is s divided by s square plus omega square. So in that expression, we replace s by s minus a. So it should be s minus a divided by s minus a whole square plus omega square. Okay. Similarly, the Laplace transform of e to the power at sine omega t. This is, what is the Laplace transform of sine omega t? The Laplace transform of sine omega t is omega divided by s square plus omega square. So instead of s, we write s minus a. So this will be omega divided by s minus a whole square plus omega square. Okay. Let us look at another example. Laplace, inverse Laplace transform of s plus 1 whole square plus omega square. Okay. This is equal to, this is of the form s by s square plus omega square with s replaced by s plus 1. Okay. So this is nothing but cos of omega t multiplied by e to the power minus t. So here e to the power at, here a is minus, there is minus 1 times t. A is minus 1 and this is cos omega t. Similarly, Laplace inverse omega by s plus 1 whole square plus omega square. This is nothing but e to the power minus t sine omega t. Because the Laplace transform of sine omega t is omega by s square plus omega square, and because of this minus t, we have s minus 1, so there is s plus 1 whole square. Okay. So this is an application of this first shifting theorem. Okay, that is fine. Then let us look at another example. Find the inverse of the transform. Find the inverse of the transform (3s minus 137) divided by s square plus twice s plus 401. So we have to find the inverse Laplace transform of this function. So solution. Here, the given Laplace transform is this. This is 3s minus 137 divided by s square plus twice s plus 401. Now you write the denominator as s square plus twice s. So it's today to write this as s plus something whole square. So from this we can see that this is s plus 1 whole square. So s square plus twice s plus 1, that will give you s plus 1 whole square. So if we subtract that 1 from 40, we should get, sorry, 400. If we subtract 1 from 401, we should get 400. And 400 can be written as 20 square. So the denominator has been taken care of. This is s plus 1 whole square plus 20 square. Then this should be written as 3s plus 1. So this is 3s plus 3. Since we have added 3, we should also subtract 3. So minus 37 minus 3, there is minus 140. Minus 140. Okay. Now this can be written as 3 times s plus 1 divided by s plus 1 whole square plus 20 square minus 140 can be written as 7 times 20. 7 times 20 divided by s plus 1 whole square plus 20 square. So now let us take the inverse Laplace transform of this. Therefore, the required function is inverse Laplace transform of this. Inverse Laplace transform of 3 s plus 1 divided by s plus 1 whole square plus 20 square minus 7 times 20 divided by s plus 1 whole square plus 20 square. We know that Laplace transform is a linear transform. It's a linear operator. Similarly, the inverse Laplace transform is also a linear operator. Okay, so that means this is nothing but 3 times inverse Laplace transform of s plus 1 divided by s plus 1 whole square plus 20 square minus 7 times the inverse Laplace transform of 20 divided by s plus 1 whole square plus 20 square. This is 3 times. This is 3 times the inverse Laplace transform of this. And the inverse Laplace transform of this is of the form cos omega t. Okay, where omega is 20, then we have a shifting by an amount e to the power minus t. So this is e to the power minus t cos of 20 times t minus 7 times. This is of the form sine omega t with a shifting by an amount e to the power minus t. So this is 7 times e to the power minus t sine 20 times t. So from these two terms, I can take e to the power minus t common, e to the power minus t. Okay, this is 3 cos 20t minus 7 sine 20t. Okay. Okay, so this is e to the power minus t, 3 cos 20t minus 7 sine 20t. And what does it represents? It represents damped oscillation. Damped oscillation with angular velocity omega equal to 20. And this is the exponential decay term which leads to damping. Okay, so this is fine. Okay, then next let us look at another topic. Let me take a new sheet of paper. That is Laplace transform of derivatives. Laplace transform of derivatives. This Laplace transform is a very useful method for solving ordinary differential equations and initial value problems. These operations of calculus on functions which are replaced by operations of algebra on linear transforms. So that is why we need to find out the Laplace transform of derivatives. Okay, because we want to apply this method to solve ordinary differential equations and initial value problems. So let us first write down a theorem. Theorem that is, if the Laplace transform of the function f of t is equal to f of s, and if number one, f of t is continuous. F of t is continuous for all t greater than 0. Number two, f prime t. F prime t means the derivative of f with respect to t is piecewise continuous. Is piecewise continuous. Is piecewise continuous in every finite interval. Every finite interval, there is t. Number three, f of t is of exponential order. Order for t greater than t, small t greater than capital T, that is the modulus of f of t is less than m e to the power a times t for t is greater than capital T. Then the Laplace transform of the derivative of f of t, this is equal to s times f of s minus f of 0. Okay, so this is the Laplace transform of the derivative of a function. This is equal to s times Laplace transform of the function minus the value of the function at t equal to 0. We can prove this very simply. Here we should write here where real part of s is greater than a. Let us prove this. Proof. Laplace transform of f prime of t. This is equal to, by definition, integration from 0 to infinity e to the power minus st f prime t dt. Now let us integrate this by parts. Okay. So integrating by parts. Integrating by parts, we have this Laplace transform of f prime t. This is equal to, so let us take this as the first function and f prime t as the second function. Okay, so this is the first function multiplied by integral of the second function, that is f of t, calculated at 0 and infinity, plus now this is actually minus, but differential of the first function. So we get another minus s from here. So we get plus here. Okay, so s times e to the power minus st, then integral of the second function f of t dt. Okay. And since f of t is of exponential order, the value of this expression at the limit t tends to infinity, this is 0. Okay, so what remains is only the value of this expression when t is equal to 0. I repeat, this expression when it says at t equal to infinity, so what remains is only the value of this expression at t equal to 0, the lower limit. So minus f of 0, because the value of e to the power 0 is 1, and so we have only minus f0 plus s times, and this is from 0 to infinity. And what is this? This is the definition of the Laplace transform of f of t. So this is s times f of s. Okay, for this real part of s greater than a. Okay, so the Laplace transform of derivative is s times fs minus the value of the function at the origin. Okay, so let me write it on a new sheet of paper. For the cases where f of t has a finite discontinuity, at t equal to 0, resulting in a delta function in the derivative, care must be taken to identify the two cases at t equal to 0. That is, number one, t tends to 0 from the left. That is just before t equal to 0. And number two, t tends to 0 from the right. That is just after t equal to 0. So for a case where we have a finite discontinuity at t equal to 0, that means this the value of the function when we approach when we approach the origin from the left, that is the left hand limit and the right hand limit are not equal. Okay, so for a case where the left hand limit and the right hand limit are not equal at the point t equal to 0, we must take care to identify the two cases. That is the t when we approach from the origin from the left, that is, and another is when we approach the origin from the right. Let us look at one example of this. Consider the function f of t to be the unit step function. Then it is something like this. This is f of t. This is t. And for all values of t less than 0, the function is 0. And for all values of t greater than 0, the function is 1. Okay. Consider this unit step function. So it is this function. Here we have a finite discontinuity at the origin. Okay. The derivative f prime t, the derivative of the unit step function is given by delta function, delta t. Okay, so the Laplace transform of f of t, we know that is the Laplace transform of the unit step function, and we already know that it is 1 by s. Okay, then let us apply the rule for the Laplace transform of derivative. Applying the rule, what is the rule? The Laplace transform of the derivative is equal to, there is a Laplace transform of, what is the derivative? That is delta t. Laplace transform of delta t, there is minus f0 plus s times f of s. Okay, this is the Laplace transform of derivative, that is sfs minus f of 0. Now let us calculate this sf, the Laplace transform of derivative. Fs, we already know it is this 1 by s. Okay, now let us calculate the Laplace transform of this derivative. Now, if t equal to 0 is taken to be the left hand limit, that is 0 minus, then we have the Laplace transform of delta t. This is equal to, when we approach f from the left, this is 0 plus s times 1 by s. S times 1 by s. F of s is 1 by s. This is equal to 1. Okay. If second case, if t is equal to 0 is taken to be 0 plus, there is the right hand limit, then the result becomes that is this f of 0, that is the value of the function at t equal to 0, and if we take this to be the right hand limit, then it is 1. So Laplace transform of, I repeat, if we take this f of 0 as the right hand limit, then we approach 0 from the right and the value is 1. Okay. So Laplace transform of delta t, this is equal to, here we have a minus sign here, so it will be minus 1 plus s into 1 by s. This is minus 1 plus 1. This is equal to 0. So for this particular case, we have Laplace transform of delta function is 1 if we take the left hand limit, if we take this value as the left hand limit, and if we take this value as the right hand limit, then we get the value 0. I repeat, if we take this value as the left hand limit, we get the Laplace transform of delta function is 1. And if we take this as the right hand limit, we take the Laplace transform of delta equal to 0. Okay, that is fine. So let me take another sheet of paper. What will be the Laplace transform of the second order derivative of f? Okay, the Laplace transform of the second order derivative of f, this is given by s square Laplace transform of f of t minus s times the value of the function f at t equal to 0 minus the derivative of the function calculated at the point t equal to 0. Okay, this can also be written as s square f of s minus s capital F at 0 minus the derivative of capital F calculated at 0. This formula holds if Ft and F prime t are continuous for all t greater than equal to 0 and satisfy the growth restriction. That is, they are of exponential order. And F double prime t, that is the second order derivative, is piecewise continuous. Is piecewise continuous on every finite interval in the semi-axis. In the semi-axis, t greater than or equal to 0. Okay, this is fine. This is okay. Okay, let us look at one application of this example. Let the function be t sine omega t. Find the Laplace transform of f. The function is t sine omega t. Find the Laplace transform of f. Okay. We have not come across any formula to calculate this so far. So let us apply this particular formula. I repeat, we have not come across any formula to calculate this directly. So let us apply this formula. Okay, that is a Laplace transform of the second order derivative. Here we have the Laplace transform of the second order derivative is equal to s square f of s minus s f of 0 minus f prime 0. Okay. And what is the value f of 0? Here the function is t, so sine omega t. So when t is equal to 0, this is 0. So f 0 equal to 0. So this is 0. And now let us calculate f prime t. F prime t is this derivative of this. So first, this is, if I differentiate this first, I have sine omega t plus, now if I differentiate this, I have omega t cos omega t. Okay. From this we have f prime 0. Now you put t equal to 0. Okay. To calculate this, you put f prime 0. T equal to 0, this is 0. T equal to 0, this is 0. Therefore, f prime 0 is also 0. So this is 0, this is 0. Okay. Now let us calculate f double prime. F double prime. This is, if you differentiate this again, okay, what will you get? If you differentiate this again, this you will get omega cos omega t plus omega cos omega t minus omega square t sine omega t. This is nothing but twice omega cos omega t minus omega square t sine omega t. Okay. Now let us take the Laplace transform of this. Okay. So therefore, if I take the Laplace transform of this, we get twice omega Laplace transform of cos omega t minus omega square Laplace transform of t sine omega t, and this is what we want to calculate. This is equal to, from this is 0, this is 0, this is s square Laplace transform. Okay, this is s square Laplace transform of, what is f of s? F of s is Laplace transform of f of t, that is Laplace transform of t sine omega t. So Laplace transform of t sine omega t. Okay, minus 0. These terms are 0. So this implies you can combine these two terms. So this implies s square plus omega square Laplace transform of t sine omega t. This is equal to Laplace twice omega. Laplace transform of cos omega t is s divided by s square plus omega square. Therefore, Laplace transform of t sine omega t, this is equal to twice omega s divided by s square plus omega square whole square. So this is the answer. So this is how we calculate Laplace transform of t sine omega t by using the Laplace transform of second order derivatives.